Now, let's look at a potential energy diagram to explain this formula right over here. So you recall that, hopefully y'all recall, that a reaction, when you have a reaction, what happens is that you start at your reactant's potential energy, right? The potential energy of the reactants is here. Then what happens is the reactants have to absorb energy in order to overcome an energy barrier, which is known as the activation energy. Then after that, some energy is released, and then our products are formed. All right, this is how a chemical reaction goes. Now, what's happening? What do you think is happening in sort of this part of the equation, or not the equation, but what do you think is happening on this part of the graph? Well, what's happening on this part of the graph is that bonds are being broken. All right, this is why it takes energy, right? Because if you have a sort of covalent bond where A is bonded to B, if you want to break this covalent bond right over here, that's going to take energy. So as bonds are being broken, if I try to break this bond, well, first of all, it's going to start absorbing that energy that I put in, right? So bonds are being broken, energy is being absorbed. Now, once you go over this activation energy barrier, well, then as new bonds are formed, so let's say if I add another atom example, as new bonds are being formed, right? This is a new covalent bond being formed between B and C. What's going to happen is energy is going to be released. So this um, energy is going to be released as new bonds form. So this part of my graph right over here, bonds are being formed. What is the delta H of our reaction? The delta H is simply just the difference between the potential energy of where you started versus the potential energy of where you ended, right? It's going to be this value right over here. This is your delta H value, your change in energy, enthalpy, sorry. Change in enthalpy, change in potential energy, or a lot of times you call it the heat of the reaction, right? Because it measures how much heat is given off from a reaction. I mean, in this case, right, notice how the potential energy of our products is more than the potential energy of our reactants. So this reaction is absorbing energy, right? I mean, right, this reaction, it's absorbing energy, and we call this an endothermic reaction. But notice how, look, essentially, right, what's going to happen is your change in enthalpy is basically just going to come down to how, right, the bond's broken. It's this part right over here. It's this distance right over here. It takes this much energy in order to break our bonds. Now, as new bonds form, well, what's going to happen is that some of the energy is going to be released, right? It releases this much amount of energy. Therefore, our change in our potential energy is just going to be this distance right over here. Therefore, we kind of have a formula to estimate the delta H of our reaction, or our heat of reaction. So this is going to be just our heat of reaction is basically going to be the amount of energy it takes to break all the bonds, right, in my chemical reaction. That's going to be subtracted by the amount of. Now let's talk about this formula in a little bit more detail. Let's talk about bond enthalpy first. Let's get a little review on that. It's defined as the amount of energy required to break 1 mole of a specific bond in the gas phase. So when you're thinking about bond enthalpy, you should be thinking about gas phase. Okay. Now let me give you an example. So let's say if I have CH4, and this is CH3, and this is going to be H. All right, and everything in my reaction here is going to be in the gas phase. Okay. Right over here, let's just visualize what's happening. So we have CH4, and this is methane. And what's essentially happening is we're turning this into CH3. There's going to be 1 electron here. It's going to be plus this. But what I do want y'all to focus on is the fact that when we want this reaction to occur, what's essentially happening is that we need energy to break this bond, right? That's essentially what the reaction is happening, right? When we break this bond, then we're just left with CH3 and then a single hydrogen. And it turns out that the amount of energy it takes to break 1 mole of this specific bond, in this case, this CH bond, right? If we're trying to break the CH bond, turns out that if we want to break 1 mole of this CH bond in the gas phase, well, it's going to take 412 kilojoules per mole. And that is basically definition. Now, the thing about bond enthalpies is that, in fact, it's maybe not accurate enough to just say bond enthalpy. Maybe it's more accurate to say this is the average bond enthalpy. Okay. So if I were to, let's say, have a molecule of ethane, if I wanted to break this bond right over here, notice how I'm also trying to break another CH bond. However, it's going to be a little bit different than breaking the CH bond right over here. Breaking the CH bond right over here takes about approximately 413 kilojoules per mole, all right, for a molecule of methane. Now, for a molecule of ethane, this takes about, pretty sure it's about 410 kilojoules per mole. So notice how it's slightly different. All right, but what we essentially do is we take the values for breaking the CH bond, right? We take all of these energy values and we basically take the average of them. So we get 412 kilojoules per mole. And this gives us a really good estimate of the delta H in the reaction. So this is why a lot of times when you're doing kind of bond enthalpy problems, right, it's not going to be a perfect, perfect enthalpy kind of value, right? There's going to be a little bit of error. And that just comes from the fact that this is the average bond enthalpy. All right, it's not the exact bond enthalpy for this specific compound. All right, it's the average of all of these bond enthalpies. The simple problem using this formula, and we'll work our way up there. Let's say if we have CH4 breaking into one singular carbon atom and 4 individual hydrogen atoms. Now, first of all, let's just visualize how this is looking. All right, off with methane, and we're just left with a single carbon and 4 hydrogen atoms. Now, in order for this reaction to work, what has to happen? You essentially have to break all these bonds, right? You have to break all these bonds. So in this case, I have to break 1 CH bond, 2 CH bonds, 3 CH bonds, and 4 CH bonds, right? Notice how I have to break 4 CH bonds. Now, how much energy does it take for me to break a single CH bond? 412 kilojoules per mole. So let me multiply 4 by 412 kilojoules per mole. Kilojoules per mole. And yeah, that's going to be my answer. It's going to take this much energy in order for me to break all of these bonds right over here, right? Notice how this fits with this formula that I'm using. Because look, the delta H of our reaction is going to be the sum of all of the energy it takes to break these bonds minus the amount that was formed. Notice how no new bonds formed in the end of our reaction, right? Notice how there was no new bonds. Everything just broke up, right? So essentially, we have 0. It took 0 energy to form anything because we did not form anything at all. And notice how it took the sum of all of the bond enthalpies that are broken is 1648 kilojoules per mole. So 1648 minus 0 is going to give me 1648, right? So if nothing is formed, if no new bonds form, well, we're just going to use this part of the formula because this essentially zeroes out. It's very good to just draw out a visual diagram to see what's going on. So we have CH3Cl, and this is going to look like this. Remember, carbon likes to form 4 bonds. Halogens, hydrogens, they form 1 bond. So you're going to have CH3 and then the Cl, and you're going to react this with H2, which looks like this. And this is going to yield CH4, and HCl. Now, visualize what's happening. All right, what do you think has happened in order for these reactants to turn into the products? All right, what do you think happened? Well, the first thing that has to happen is that, well, this hydrogen bond has to break up. All right, so this H bond has to break up. And another thing that has to happen is this CCl bond also has to break up. This carbon and this chlorine bond has to break up, right? Notice how at the end, there's no chlorine here, right? There's hydrogen that's substituted for it. And how do we get the hydrogen? Well, first we have to break up this bond, right? So that's how I kind of think about it, right? We have to break up these 2 bonds first before we can, start anything, right? Before things can happen. All right. And what has formed as a result? So what has been created as a result? Well, as a result of these bonds breaking right over here, well, a new bond has formed. A new CH bond has formed, right? This initially, this broken off hydrogen has now attached to this carbon. So that is a new bond that formed. And another bond that formed is this HCl bond, right? This HCl bond was not there before. One of the hydrogens decided just to bond with this chlorine right over here. So these are the bonds that are broken, and these are the bonds that are formed. Now, what is the sum of the bond enthalpies that are broken? Well, notice how CCl, that's 328, and in HH, that's going to be 436 kilojoules. These are our bonds that are formed. So what has formed? CH. CH is 412 kilojoules per mole. And what about HCl? HCl, well, HCl, in order for that to form, 431 kilojoules per mole. Kilojoules per mole. All right, so these are our bonds broken, and these are our bonds that are formed. So this is bonds broken, and these are bonds formed. Now what I have to do now is just subtract these two values, right? Just subtract these two values, and you would get the answer. Make sure if you're using a calculator, put these in parentheses. So make sure you're distributing this negative sign to the whole thing. Okay. My calculator gives me negative 79 kilojoules per mole. And all this negative 79 kilojoules per mole is saying is that when we have this reaction occurring right over here, that's going to release 79 kilojoules of heat. All right. And because this is the negative sign right over here, we're releasing heat. Remember, negative sign means that we're releasing heat. AKA, this reaction is something known as an exothermic reaction. Heat is being released. All right. So when 1 mole of this reacts with 1 mole of this to produce our products, that much heat is going to be released. And if I were to graph this on a potential energy diagram, so I messed that up. There we go. That's much better. So if on our x-axis we have the progress of our reaction, and our y-axis we have our potential energy, well, because our delta H right over here is a negative value, that means that we have lost heat, right? We're releasing heat to our surroundings, which means that as a result, we're going to be losing heat than we originally started with. The potential energy of our reactants is going to be higher than where we ended, because when we ended, we released a lot of heat, right? Now you might be saying, okay, this is a cool formula and everything for estimating the delta H value, but what if I want to find a delta H value where my methane was a liquid? You can have liquid methane. Now, what if you wanted to do that, right? Originally, we calculated that the delta H for this reaction was approximately negative 79 kilojoules per mole. All right, and that's great and all, but what if I wanted this reaction where you have this reacting into methane that's liquid and HCl? I haven't changed my products or my reactants except for this methane right over here that's liquid. Then how would I do this? Well, the thing is that first what I can do is I can say, okay, we have this original reaction here. How much energy does it take for methane to condense? All right, how much energy does it take for methane to become a liquid from a gas? Okay, and it turns out that it's approximately I'm pretty sure it's negative 8.2 kilojoules per mole. So in order for methane to become from a gas to a liquid, it takes approximately negative 8.2 kilojoules per mole. Now, what I can do now is I can add these two reactions up together. And when I add up these two reactions together, I'm also going to add up the change in enthalpy. So the change in enthalpy for the first reaction right over here is going to be negative 79 kilojoules per mole. And the change in enthalpy for the second reaction is negative 8.2 kilojoules per mole. So if I add up these two reactions right over here, negative 79 plus negative 8.2 kilojoules gives me negative 87.2 kilojoules per mole. And notice how also when I add these two reactions up together, I have a methane on my reactant side that's in the gas phase, and I also have a methane on the product side that's on the gas phase as well, right? I have one in the reactant side, I have one in the product side. So I can cancel them out. And look what I get. I get CH3ClH2 gas, and that's going to yield CH4 liquid, and HCl gas. So notice how I get the exact same reaction that I'm looking for by adding up these two equations together. All right. And this is just a preview for the next video, which is something called Hess's law. And it basically just states that, right, if we can write out a reaction as multiple steps, well, then the total sort of enthalpy change is going to be the sum of all the individual enthalpies for that reaction. And that makes intuitive sense, right? It takes this much energy for this reaction to occur and this much energy for this reaction to sort of occur. Then, well, if you add these two enthalpies up together, you're going to get the total net energy for all these reactions to occur, aka this reaction right over here, right?